This chapter introduces to the term reverse engineering and to the associated techniques that can be used for scanning physical parts. In addition, the chapter presents the process of reverse engineering and the strategy for scanning and converting the scanned data into a 3D surface or solid model. Engineering is the process of designing, manufacturing, assembling, and maintaining products and systems. There are two types of engineering: forward engineering and reverse engineering. Forward engineering is the traditional process of moving from high-level abstractions and logical designs to the physical implementation of a system. In easy words, for example, if we want to do reverse engineering of a pen, first we need to have actual pen. By help of measuring instruments, a 3D model is created in CAD software. The next step for it will be making a 2D drawing for manufacturing and then making assembly drawing. In some situations, there may be a physical product without any technical details, such as drawings, bills of material, or without engineering data. The process of duplicating an existing part, sub-assembly, or product, without drawings, documentation, or a computer model is known as reverse engineering. In today's intensely competitive global market, product enterprises are constantly seeking new ways to shorten lead times for new product developments that meet all customer expectations. Reverse engineering is now considered one of the technologies that provide business benefits in shortening the product development cycle. RE allows the possibilities of closing the loop between what is as designed and what is actually manufactured. Reverse engineering is also defined as the process of obtaining a geometric CAD model from 3D points acquired by scanning existing products. Reverse engineering is now widely used in numerous applications, such as manufacturing, industrial design, and jewelry design and reproduction. For example, when a new car is launched on the market, competing manufacturers may buy one and disassemble it to learn how it was built and how it works. As products become more organic in shape, designing in CAD becomes more challenging and there is no guarantee that the CAD representation will replicate the sculpted model exactly. Reverse engineering provides a solution to this problem because the physical model is the source of information for the CAD model. This is also referred to as the physical to digital process. Another reason for reverse engineering is to compress product development cycle times. By using reverse engineering, a three-dimensional physical product or clay mock-up can be quickly captured in the digital form, remodeled, and exported for rapid prototyping / tooling or rapid manufacturing using multi-axis CNC machining techniques. Why use reverse engineering? Following are some of the reasons for using reverse engineering. The original manufacturer no longer exists, but a customer needs the product. For example, aircraft spares required typically after an aircraft has been in service for several years. The original manufacturer of a product no longer produces the product. For example, the original product has become obsolete. The original product design documentation has been lost or never existed. Inspection and quality control, comparing a fabricated part to its CAD description or to a standard item. Some bad features of a product need to be eliminated. For example, excessive wear might indicate where a product should be improved. Strengthening the good features of a product based on long-term usage. Analyzing the good and bad features of competitors' products. Exploring new avenues to improve product performance and features. Creating 3D data from a model or sculpture for animation in games and movies. Creating 3D data from an individual, model or sculpture to create, scale, or reproduce artwork. Generating data to create dental or surgical prosthetics, tissue-engineered body parts, or for surgical planning. The above list is not exhaustive and there are many more reasons for using reverse engineering than documented above. Reverse engineering, the generic process. The generic process of reverse engineering is a three-phase process. The three phases are scanning, point processing, and application-specific geometric model development. Phase 1: Scanning. This phase is involved with the scanning strategy, selecting the correct scanning technique, preparing the part to be scanned, and performing the actual scanning to capture information that describes all geometric features of the part such as steps, slots, pockets, and holes. Three-dimensional scanners are employed to scan the part geometry, producing clouds of points, which define the surface geometry. These scanning devices are available as dedicated tools or as add-ons to the existing computer numerically controlled (CNC) machine tools. There are two distinct types of scanners, contact and non-contact. Contact scanners. These devices employ contact probes that automatically follow the contours of a physical surface in its current marketplace. Contact probe scanning devices are based on CMM technologies, with a tolerance range of plus 0.01 to 0.02 mm. However, depending on the size of the part scanned, contact methods can be slow because each point is generated sequentially at the tip of the probe. Tactile device probes must deflect to register a point, hence, a degree of contact pressure is maintained during the scanning process. This contact pressure limits the use of contact devices because soft, tactile materials such as rubber cannot be easily or accurately scanned. Non-contact scanners. A variety of non-contact scanning technologies available on the market capture data with no physical part contact. Non-contact devices use lasers, optics, and charge-coupled device (CCD) sensors to capture point data. Although these devices capture large amounts of data in a relatively short space of time, there are a number of issues related to this scanning technology. The typical tolerance of non-contact scanning is within plus or minus 0.025 to 0.2 mm. Some non-contact systems have problems generating data describing surfaces, which are parallel to the axis of the laser. Non-contact devices employ light within the data capture process. This creates problems when the light impinges on shiny surfaces, and hence some surfaces must be prepared with a temporary coating of fine powder before scanning. These issues restrict the use of remote sensing devices to areas in engineering, where the accuracy of the information generated is secondary to the speed of data capture. However, as research and laser development in optical technology continue, the accuracy of the commercially available non-contact scanning device is beginning to improve. The output of the scanning phase is point cloud data sets in the most convenient format. Phase 2 point processing. This phase involves importing the point cloud data, reducing the noise in the data collected, and reducing the number of points. These tasks are performed using a range of predefined filters. It is extremely important that the users have very good understanding of the filter algorithms so that they know which filter is the most appropriate for each task. This phase also allows us to merge multiple scan data sets. Sometimes, it is necessary to take multiple scans of the part to ensure that all required features have been scanned. This involves rotating the part, hence each scan datum becomes very crucial. Multiple scan planning has direct impact on the point processing phase. Good datum planning for multiple scanning will reduce the effort required in the point processing phase and also avoid introduction of errors from merging multiple scan data. A wide range of commercial software is available for point processing. The output of the point processing phase is a clean, merged, point cloud data set in the most convenient format. This phase also supports most of the proprietary formats mentioned above in the scanning phase. Phase 3: Application Geometric Model Development. In the same way that developments in rapid prototyping and tooling technologies are helping to shorten dramatically the time taken to generate physical representations from CAD models, currently re-technologies are helping to reduce the time to create electronic CAD models from existing physical representations. The generation of CAD models from point data is probably the most complex activity within RE because potent surface fitting algorithms are required to generate surfaces that accurately represent the three-dimensional information described within the point cloud data sets. Most CAD systems are not designed to display and process large amounts of point data. As a result, new RE modules or discrete software packages are generally needed for point processing. Generating surface data from point cloud datasets is still a very subjective process, although feature-based algorithms are beginning to emerge that will enable engineers to interact with the point cloud data to produce complete solid models for current CAD environments. This phase depends very much on the real purpose for reverse engineering. For example, if we scanned a broken injection molding tool to produce a new tool, this involves importing the as-designed CAD model and superimposing the scanned point cloud data set of the manufactured part. The RE software allows the user to compare the two data sets, as designed to as manufactured. This process is also used for inspecting manufactured parts. Reverse engineering can also be used to scan existing hip joints and to design new artificial hips joint around patient-specific pelvic data. This creates the opportunity for customized artificial joints for each patient. The output of this phase is geometric model in one of the proprietary formats such as IGES, VDA, STL, DXF, OBJ, VRML, ISOG code, etc. This chapter defined the term reverse engineering followed by reasons for using reverse engineering. It also introduced the reverse engineering strategy, the three phases of the reverse engineering generic process: contact and non-contact scanning, point processing, and application of geometric model development. Reverse engineering strategy must consider the following. Reason for reverse engineering a part. Number of parts to be scanned, single or multiple. Part size, large or small. Part complexity, simple or complex. Part material, hard or soft. Part finish, shiny or dull. Part geometry, organic or prismatic and internal or external. Accuracy required, linear or volumetric. With this we end our video. Our next video we will discuss various types of process involved in 3D printing. Thank you.